Question 12 then from the 2016 Advanced Higher Mathematics of Mechanics. 8-mark question this time. Well, a little diagram, but a velocity diagram, not an actual map diagram. So that's going to be the resultant speed of the aircraft, the resultant velocity of the aircraft. Now it said, maybe I need more space in this, it set off at a bearing of 110, so from north that means it's heading 10 degrees south of that line. But what we'll have to do is figure out what is the resultant speed, because you know that it travelled, so I can work out the speed part of that. The speed part would be it did 1,080 kilometres in 2 hours and 15 minutes, in 2.25 hours. So that gives you a nice 480 kilometres per hour. Now, since the speed of the aircraft in still air is 450, that line should be shorter than that line, which means that the velocity of the air must be going like this. So I'll call that the air, not the wind, so I'll call it W. And so that was the aircraft. There's the velocity diagram for it. The aircraft had to head 10 degrees south so that the wind carried it to its destination. Now, there's two ways you could do this. You could do this with velocities, or you could just do it with distances and angles. So it depends which kind of trigonometry you want to do. So you can either use your sine rules and cosine rules, or you could simply use components. Consider horizontal movements, consider vertical movements. I'll do the cosine business first of all. So if that's the case, I'm going to dispense with those parts and just say that was 480, just taking speeds. That was 450, and I don't know what that is. So how could I find the length of that side? Cosine rule. So W squared would be, and it takes a lot to write out. You'll see afterwards how much faster it would be if you did vectors just taking the horizontals and the verticals rather than taking them in a winner. Minus 2 times it times the cosine of the angle between 10 degrees. Now, there's no marks for all the bits and pieces, so in your calculator you're going to put square roots. So straight away from that, you press the button and you get 86.388 and so on. So there's the wind speed. The wind speed is 86.4 kilometres per hour. The way the marks were, there was a mark for constructing the diagram, which allowed you to do this, and then there's a mark for getting the answer by using your cosine rule. Now the next bit's a wee bit messier. I want the bearing of the wind. So I want the angle from north. I want this angle here. Well, I'd have to calculate the whole angle and then do some angle jiggery-pokery to get to it. So to find this whole angle, if I just call that x just now, I would have this, again just using the cosine rule, I would have cos x equals, and then that's the odd one out, so it's going to be 450 squared plus 86.4 squared minus 480 squared, all over the 2 times these two, 450 times 86.4. But of course, when you put that into your calculator, you're going to do inverse cos of all of that. And when you press equals, you get 105.236 and so on. So you get 105.2 degrees. But that's not the bearing. That's this whole angle here. So to get the bearing itself, you'll have to play about with this triangle now. So the way you would be doing that would be by introducing the norths to create parallel line angles, so that you know, for instance, that if that was 100 degrees, that part's 80. And if that part's 80 by alternate angles, that portion is 80. So that the portion you want for the bearing, that's the angle from north, it would be that whole corner, which you worked out, minus 80. So that angle must be 105.2 minus 80, which is 25.2, except in a bearing it should have three figures for the whole part, so 0.25.2. So I'll just finish that off. So what was the wind? So the wind was 86.4 kilometers per hour at a bearing of 025.2 degrees. Getting that bearing was the third mark. Now, if you today, using vectors, you could have written this down. You could have said, well, the velocity of the aircraft plus the velocity of the wind gives the resultant velocity, the one that was straight across there. And then you could put in their components, because you know the parts of it. We need a bit more room than that. So the first part would be, what were the horizontal components, if you like, the x components of them. Remember, x along is positive, y up is positive. Well, for this one here, the horizontal component of that, I'll just put in its magnitude, because that was 450 and that was 480, but I don't know what the wind was. But for this part here, the horizontal component of that is adjacent to the 10, so that would be 450 cos 10 degrees. The vertical component, notice it's going down the way, will be minus 450, and it's opposite that, so it'll be the sine 10 degrees. The wind, it's going across the way as well. Now, I don't know what its angle is. I could put in any angle I like, but I think I'll put in this angle and call that alpha, for instance, because then I can say, and that, of course, that directly would be the bearing that I want. So then I could say, well, for this one, calling W, rather than having to put the modulus in there, W, and then for the distance across the way, that would be sine alpha. It's going the proper way. And also going the proper way up the way is W cos alpha, should produce the result, which is 480 across and 0 up. Now that gives me a couple of equations then. And the unknowns are both in this part here, notice, and those are just numbers. So you could take those numbers across and subtract them and get two independent equations. So you've got W sine alpha would be 480 minus this, and you might as well just work that out in one go. So you would just do 480 minus 450 cos 10, and that gives you 36.836. Maybe I'll take it to 3 decimal places just now. And this one, W cos alpha, would be, it'll be 0 minus that, so it'll just be that. It'll just be, which gives you 78.142. That's just like you had in the higher, wasn't it, for your wave equation? So the way you would solve them would be, if you divide them, you'll have the tangent. If you square and add them, you'll get that one. So what I'll do the W first, that's its magnitude. So if you do 1 squared plus 2 squared, you'd end up with W squared equals 36.837 squared plus 78.142 squared. Of course, you're just going to do square root of that. And when you do that, you get 86.389, which is 86.4 kilometers per hour. And if you divide them, if you do 1 divided by 2, the W's you cancel, that becomes tan, and you've just got tan alpha will be 36.837 over 78.142. But of course, you're just going to type in inverse tan of that. And if you do that, you get 25.239. So it's the same answers. So the magnitude is that, and of course the bearing is 025.2. It's actually slightly neater because you don't have to use your cosine rules or anything like that. And then part B of this then. Well, there's a wee part here at the beginning. Given that the velocity of the wind remains constant, why is the return journey longer? For part 1, well, if the wind stays the same, it means when you fly back, you'll be flying against it. So obviously it's going to slow you down. So you could say fly against the wind. Not completely against it, but certainly against a component of it. On return, that would do, wouldn't it? You fly against the wind in return, so that means the net speed is slower. Do you have to say that? It means net speed, I shouldn't have said net, I should have said resultant. Resultant speed is slower. That's worth a mark. Now, you've actually got to work out how much slower that's going to be. So that means there's going to be another diagram and so on. And again, there'll be two ways. You can either use your distances and angles in a triangle and sine and cosine rules, or you can do it the vector way. So you're going back this time. Remember, this is going to be speeds I'm putting down here. I'll just put a wee direction in anyway. If you're heading back from Copenhagen to Glasgow and the wind's still blowing like this, you're going to have to head down to get blown up. And that line will have to be longer than that one if the wind's going to blow you back up. So putting in the figures, that was 450. I had a note of them there. Yeah, oh, there they are. So the aircraft's going at 450. The wind's going at 86.4, and I want to work out this speed here. Now, if I'm going to do it the sines and cosines way, I need angles, specific angles inside the triangle. So that means I'll have to do some working out to begin with. Now, I know this angle here is 25.2, so using the norths to get alternate angles, that's going to be 25.2. Need to fix this down. And since that's north-south and that's east-west, that's a right angle, which means I know this angle in here. It'll be 90 plus 25.2, which is 115.2 degrees. But that's not going to give me V directly. I've got an opposite pair here. To get V, I need the angle opposite to it. So I'll have to find this angle first in order to get this angle, and from that angle I can get V. So there's a bit of messing about. So if I call that alpha first of all, then to get this angle I can use the sine rule. So sine alpha over its corresponding side, 86.4, is the same as the sine of the one you know, 115.2, over its corresponding side, 450. But the sine rule works both ways round. Which means to get alpha, it would be take that across and then get rid of sine. So it's inverse sine of 86.4 sine 115.2 over the 450. And then it's press the buttons. And when you do that, you get 10.000, so that's 10 degrees. Which means that the angle I actually want, if I call that beta, will be the triangle, don't know why I wrote that, that was messy, which is 180 minus what you've got so far, the 115.2 plus the 10 degrees, so that's 54.8. So far, apart from that being 1 mark for constructing the diagram so you can see what's happening, 1 mark for going through the sine rule to arrive at the 10. Now the next mark would be for getting the speed. So to get the speed, you could use the sine rule, or you could just go in with the cosine rule. V squared would be 86.4 squared plus 450 squared minus 2 times them. Whoops. Times the cosine of the angle in between, which you now worked out to be 54.8 degrees. But of course you can do the square root of that, but I'm not going to write it all again, square root of that. I'll just do square root of it. And you get 406.376 and so on, which isn't a final answer, so you could just leave it that way and call that kilometres per hour for the resultant speed. You could put that down. Resultant is that. Getting that is worth a mark, and you can round it off if you like, but it's not a final answer, it's just an intermediate one, so I'll just keep it like that. Because the question says how much longer, so I'll need to work out the time. Well, the time will be 1080 divided by that, 406. I think I'll put 406.38, but I'm actually just going to use answer to put in this part of it. So just pressing in answer gives you 2.657 and so on hours. But again, that's no use. I'm just going to press now the degrees, minutes and seconds button here, which is the same as hours, minutes and seconds. And that tells me that's 2 hours, 39 minutes and 27 seconds. But it's said to the nearest minute, so that's going to be 2 hours, 39 minutes. Now it all depends how you round it off. If you round it off a bit more than that, then you can get 2 hours 40. If you just call that 2.66 for instance. But I think if you keep the accuracy, it makes a difference of a couple of seconds, actually makes it 2:39, which means the amount it takes longer then will be, well, it took 2 hours 39. Before it just took 2 hours 15, so that's 24 minutes longer. Or 25 if you rounded that off and made that 2 hours 40 by having a few extra seconds. That would be the final mark. Or there's a vector way, which, even though it might look as if it takes as long, I think it's much more elegant. So let's put down a vector equation for this then. So there's the return velocity. There's the velocity of the aircraft. There's the velocity of the wind. And I know that the magnitudes of those, the magnitude of that was 450, and I know the magnitude of that was 86.4. And if I'm going to do it the vector way, I'm just going to use components, horizontal and vertical. So I just need their angles, any angles, either to the vertical or to the horizontal. So that's quite handy here, because if that's at 25.2 to north, that means this angle here is 25.2 degrees, and that will do. I don't need to work out anything inside. What's the 450 though? I need an angle either to the horizontal or the vertical. I'll just stick with that being alpha. But doing it this way, I won't actually need to work out that alpha. I'll be able to get the magnitude straight away. And I'm just going to write V for the magnitude, meaning this, because that's just the small case letter on its own. Right, so what's the vector equation? Well, the velocity of the aircraft plus the velocity of the wind equals the resulting velocity. So let's put that down. So across the way, x direction first of all, this is going backwards and downwards. So negative 450, and the horizontal's next to alpha, so that'll be cos alpha. Down the way, it's negative 450, and that must therefore be sine alpha. Plus the wind, now the wind's across and up, so they're all positives, 86.4. If I'm using the 25.2 there, the across is opposite the angle, so that's sine. Sine 25.2, so it must be 86.4 cos 25.2. And that should equal, now notice this magnitude is actually going backwards, so I'm taking care of that here, minus V, since it's horizontal and it's got no vertical component. Now it looks like you've got two unknowns, so that to find V, you'd need to find alpha, but you don't. You could rearrange those equations just to say this. Like, take this one. I'm going to take this over here and bring that over there. So taking this over here, I've got 450 cos alpha equals V plus whatever that comes to. And that comes to 36.787 I'll put down. Same with this. Take that across, and I've got 450 sine alpha equals whatever that comes to. And here's where you'd think it'd be handy if these numbers are getting used all the time, if you had them stored under memory, like memory A, B, C, D, so you could just type in A, B, C, D instead of the whole numbers. Anyway, whatever that comes to, and that comes to 78.177. So there's two equations with two unknowns. But if you do that same thing that you're used to with that wave equation, if you do 1 squared plus 2 squared, then that just becomes 450 squared equals V plus 36.787 squared plus 78.177 squared. Now that might look as if I'll multiply that all out and get some quadratic with nasty coefficients in it, but you don't need to do that because there's only one mention of V. To get to V, I just need to get rid of this by subtracting it, take the square root, and then finally subtract that number. So I'll do it in 2 bits. So V plus 36.787 squared would be that squared minus that squared, which comes to quite a big number, 19638 we'll call it 36. Now, when you do the square root, you're going to get a positive or negative, but V is a positive amount. Now, the square root of that far exceeds this number, but you're going to be subtracting it anyway, so that negative is just going to get more negative. So you're only going to be taking the positive root here to obtain a positive value for V. As I've already said, it's going backwards. So I could just put it down straight away then. So it'll be the square root of that minus the 38.787, and that gives me the figure 406.370, and so on. So V equals 406.37. You'll get a variation in these decimal places, of course, depending on where you round things off. So they've got a slightly bigger answer, I think, in the marking scheme, because they've rounded off more earlier. And from that was the same answer as before. Then it's just etc. to find the time. 1080 divided by that answer gives you that 2.657, the same as before. So if you call it 2.66, you'll get 40 minutes. And if you call it that itself, you'll get the 39 minutes. So it just depends how you round off. Just think this is more elegant doing it this way, since you didn't have to figure out angles in the triangle in the first place.